Okay, good afternoon. We are in the middle of the discussion about congestion control issues. If I'm not wrong, we stated that there are different techniques that can be adopted to try to solve somehow the congestion problem. And we also have emphasized that in frame relay this is an important issue because according to the service interface between the user and the network, a proper management of a frame relay network should avoid any congestion. So if congestion happens, it's something that the network should take care of in some way. We summarized the features available in frame relay, which I remember to you, it does not implement any flow control mechanism. And this may be a further problem with respect to the congestion control issue for a reason that I will try to describe in a second. Okay, so suppose we analyze for a moment the internal structure of a switch. So let's consider a generic switch. And typically what happens is that, okay, we focus on one link, and we know that typically that's the most common solution. We have buffers devoted to store packets willing to be forwarded on this link. Let's call it output link J. Okay? And of course, you may receive packets from any input link willing to be routed toward output J for some routing choice. Now we know that we may have a buffer overflow problem. Okay, when we have congestion, we start storing packets as long as we have enough buffer available, and then when the buffer is saturated, we start dropping packets. Okay, that's one way of behaving. Normally, in this architecture, you have very small amount of buffering here, just the temporary buffer storage you need to receive one packet while you are processing the previous packet on that link, making the route decision before forwarding to the proper output. So typically the memory at the input is considered to be negligible, or just that small amount that allows you to really manage the packet at the input before moving them to the output. But almost these buffers are always empty, and they are of very, very little size, just to keep a couple of packets just for some temporary issues that you may have. So what's going to happen when this buffer output Q, let's call it Qj, saturates? Well, typically if you try to forward to this queue some packets that you are receiving from input port, they are dropped, they are discarded. There is another alternative, okay, and the alternative is trying to exploit as much as possible the amount of buffering that you have in a switch. So the idea is to say, no, when I saturate or I'm close to saturation in this output buffer, I will send a back signal, which is called back pressure. This is an internal back pressure, okay, which basically is telling to the upstream links that you are not able to receive any packet. Okay, so basically you are asking the transmitter at the input port of the switch not to forward those packets, okay, instead of dropping them. That's an alternative. What's going to happen in this case? Well, this limited amount of buffer spacing is typically very quickly saturated, but suppose that you have a flow control mechanism now in this switch through the protocol architecture. Remember what flow control means. A slow receiver asking a transmitter to slow down or up to the point in which you ask to stop if you don't have enough buffer space, correct? That's the flow control. The receiver, okay, monitors its buffer occupancy. If it sees that it's not able to empty the reception buffer because you are a slow receiver, you don't have enough CPU for any reason, you ask the transmitter to slow down or even to stop. We have seen example of this flow control while we were revising layer 2 protocols. Yes. The flow control is a link problem. So it's the Yeah. What I'm assuming is that what's going to happen in this scenario if on any point-to-point link we have a protocol layer 2 which implements flow control. Maybe an ISDN channel, just to make an example, okay, something like that. So if this is true, these back pressure signals are actually created by a congestion problem that has nothing to do with flow control. Okay, you can have a congestion problem if you have no flow control issues in your network. It's a completely different problem. Congestion is an excess of traffic on a given link. That has nothing to do with a slow receiver, which is the flow control case. But through this internal back pressure mechanism, which is induced by congestion, so the cause is congestion, what's going to happen is that you will very soon trigger a flow control mechanism on these links, because you saturate very quickly these buffers, okay? And as a consequence, the flow control, now this becomes a slow receiver on this link, because you saturate the buffer, and you will send up flow control messages. So the logical flow is, I have a congestion problem. The congestion problem creates an internal back pressure signal to avoid dropping packets, which saturates the buffers at the input, which as a consequence induces and creates the flow control mechanism. Okay? This is happening if you have, first of all, this internal back pressure mechanism, which is fairly popular in switch architectures, and if you have a layer 2 or whatever layer we are talking about here that implements flow control. Of course, if you don't implement flow control, this is not going to happen. You simply will receive the packets, you will find the buffer at the input saturated, and you will drop the received packet. If you don't have flow control, this is what's going to happen. Okay? Clear up to now? Now, what's happening in a network-wide view? Well, suppose that you have all of the nodes implementing this type of internal back pressure. What's happening is that when you congest a link here, okay, you will send, flow control mechanism back to the upstream nodes, correct? Which in turn will reduce the rate of packet transmission or even stop it. They will saturate their buffers, and again, on the input link, they will send up flow control signal, and so on and so forth, until you reach the user. This is true under the hypothesis that all of the switches have internal back pressure, and on any link we have a flow control mechanism. Okay, and this is what's going to happen if we were using the ISDN B-channel architecture, okay, LabB protocol. Now, is this a good way of reacting to congestion? The answer is not. Why not? Well, because you see, we are blocking a large set of links. We are not blocking the flows which create congestion here. We are blocking the full link. So, for example, we may have a traffic flow coming from this upstream node, willing to get out on another output link, which is also blocked. So we are blocking portion of the network, a significant portion of the network, in a tree-based fashion, right? You are coming back from the congestion point in a tree-based fashion. So I'm not saying that this is a good way of dealing with congestion. This is an absolutely bad way because it's not selective. You are just blocking the full network and not only the flows that create problems, but at least there is a reaction. The network is doing something, okay? We don't even have this in frame relay because we don't have any flow control. So if we have a congestion, we have unbounded and uncontrolled losses. There is no mechanism which is automatically coming in to help somehow in solving or mitigating the congestion problem. So that's why it's very important to try to solve this problem in the LabF protocol directly. Okay, this is just a motivation why in frame relay, in the LabF protocol, there are mechanisms that allow you to deal with congestion issue. Is it clear? Do you have any question? Okay. So basically, this is what is written here. X25 or ISDN may exploit link-by-link flow control and internal switchback ratio to control congestion, but not in a proper way. It's completely unfair. It's blocking a large portion. It's not working, but still something is happening. you will reach the users which create this problem, so you will block them sooner or later, but you will block a large portion of network and a large portion of users. So what we can do better than that? So we know that we don't have, this is a summary of what I said. There are basically two mechanisms that are standardized, and those two mechanisms employ as a signaling feature 2 bits, which are a forward congestion notification bit or a backward congestion notification bit. Now I'm introducing again a very general concept. When you design any algorithm, you have also to match the complexity of the algorithm that you run with the ability of signaling information to your source. So suppose, for example, that you have a very complex, very rich algorithm that is able to compute a specific rate for each flow, for each virtual circuit. In this context, it would not be a wise choice to use it, because at the end, the only thing that you can say to the source is, I am congested, I'm not congested. That's the only information that you can. So there is no point in developing a very sophisticated algorithm, control algorithm, which has limited ability in giving this information to the user. So you have to match all of the things. So from an algorithmical point of view, you can devise many solutions. Then you have to choose, in terms of implementation, the one that better suits your technological constraint, your technological context. So in this case, we have to start from the idea that we have only one bit to signal that we have congestion or not congestion, because on one bit we have only a binary information. So that's the information that the node can send over every virtual circuit. So if you are able to manage it only to the virtual circuit that are really creating congestion, you can send this signal information, okay? But the only information that you can carry, you can transport in your network, is a binary information. Either the node is congested or it is not. That's it, okay? Clear? Okay, before we look at some of the details, let's try to say, okay, suppose that we want to solve the congestion control problem. So which are our goals? Well, informally speaking, we would like to avoid packet losses. Okay. It's not true that we would like to have empty buffers. This is not our goal. Actually, if you want to have a large, significant link utilization, the buffer should never be empty. So what we really would like to have is a network in which the buffers are always loaded with few packets, so that you keep the queuing delay low, you avoid losses, and at the same time you always have something to send so that you are able to exploit the capacity. Of course, if you have enough traffic. If you don't have enough traffic, the network is going to be underloaded, but you will not have any congestion problem. Okay. So, well, do we have any constraint? So suppose that we want to define what we would like to obtain. So suppose that we have in our hand something magic. We know everything exactly, and that's the working point over which we would like to see our network to operate. Okay? Then maybe we are not able to reach it, maybe it's too complex, but suppose that we can do that. What we would like to obtain? Well, there are several things that we may like to obtain. One is to increase or to have a significant network utilization. True, that's important. At the same time, we want to have fairness. It's not okay if we have a high utilization and we obtain this by providing a huge amount of bandwidth to a limited set of users and negligible bandwidth to a remaining part of users. That is not something that we would like to see. So, okay for what concerns the utilization, but at the same time, we would like to be fair with respect to our users. Okay? And these two goals are often contrasting. If you really want to strictly enforce fairness, very often you end up having a solution which is not optimal in terms of resource utilization. On the other hand, the solutions which optimize the exploitation of the available resources are typically not fair. So we have to balance these two somehow contrasting goals. So let's start having a very simple example. Suppose that all of the flows are alike. So we want to treat them in the same way. They don't have different requirements, okay? And what does fairness mean? Well, fairness means providing the same set of resources to all the flows, treating them in the same way. If they are have the same request, right? Now, if you have a single bottleneck, single link, that problem is trivial. You have a capacity of C on the link. You have n flows. What we would like to obtain? Each flow gets C over n. That's trivial, obvious. Unfortunately, we have to face a network-wide problem. The network-wide problem is a little bit more complex, and defining what is fair, if you don't provide a fairness definition, may not be so trivial. Let me start with this very trivial example to discuss this aspect. So in this case, you see we have a very simple network. We have only 3 links. 2 links at 10 megabit and 1 link at 45 megabit. Okay? And we have 3 flows. We have a black flow, flow number 1, which is crossing link A and link C. We have a green flow, which is only going through link B, and a red flow of 2, which is going through link A and link B. Okay? So what we would like to obtain here, well, we'll discuss it in a moment, but just give me 2 possible solutions of flow assignment. So what we are trying to say is, okay, now we have this network, we have this capacity, we know that all the flows are willing to receive the same quality, which is a reasonable rate assignment. So suppose that I can run a very complex algorithm, I have a full knowledge of what's going to happen, and I would like to assign rates to these flows. And I propose to you 2 solutions. Okay? The first one is such that I provide 5 megabit to the green, sorry, to the red, to the black, okay, flow, and 5 megabit to the red one, which are sharing this 10 megabit capacity link. And then the black is fixed to 5, so we cannot, of course, increase the rate assignment because the rate should be the same end to end. Okay? And the red is coming here with 5 megabit. I have 40 megabit left, so it makes sense to provide 40 megabit to flow 3. Now, you may say, but is this fair or not? Well, it depends on what you have in mind as fairness. If your idea of fairness is that everybody should get the same, it is not fair. In that case, you should assign 5 to everybody, but that means that any flow in your network goes to the rate, to the flow that is sending to the minimum rate, which is not really what we are interested in. So what we are interested in is to be fair with respect to the flows that are sharing the same resource, and this is what we do on link A. But if there is anything left available, why not giving it to other flows that can get more? So that's an intuitive concept of fairness, right? I give to everybody what they can, and if there is something residual, I give to the flows that can get more some additional bit rate. I'm not penalizing the other one, and I will have no gain in not giving this amount of bit rate to the other flows. You agree on that? So that makes sense. And that's one solution, and the total amount of traffic that we are carrying in this very trivial network is 50 megabit per second, right? 40 for the green one, and 5 and 5 for the red and the black. The assumption here is that we have sources that are able to inject at the maximum speed. Okay, if it is not, we can add a link, an access link to this source, and of course we will at most give to this source that access link speed, and again the remaining bitrate will be given to other flows. So that's one reasonable solution. Another reasonable solution, yes, you have a question here? We're exporting 50 megabit per second.
Yes, sorry, 50 over 65.
Yes. That is quite good, and there is actually something that we can do better. Well, if you're looking only at link or network utilization, we can do something better. This is the second solution that is reported here, in which since we give the 10 megabit to the black flow and 0 megabit to the red one, on the green link, on the link B, which is crossed by the green flow, since the red flow has a capacity of 0, we can assign 45 to the green one. So we came out with a solution which is penalizing flow 2, clearly, and is giving an overall utilization which is larger. And that's an example of what I was saying before. Increasing or trying to maximize the total utilization is another goal with respect to being fair, and then after that trying to maximize. Okay, so the first solution is more fair, but it's not maximizing the utilization. The second is instead less fair, but is maximizing the network utilization in this example. And you see that we have to take into account the network view, because one flow, consider the first assignment here, the black flow is bottlenecked at link A. Its bit rate is determined by the maximum bit rate that you can get on link A. On link C, you could get more, but since you are reaching link C after link A and you are bottlenecked there, you will reach link C with 5 megabit and you will get 5 megabit. So you see that the end-to-end rate will be dominated and will be determined by the bottleneck link rate. And the same is true for the other one. Okay? There will be no point in providing a larger bandwidth before you reach the bottleneck, because that additional bandwidth that you provide is wasted. So suppose that my bottleneck is after 4 links, and on that link I have a 10 megabit. From that link below, I will of course get at most 10, and if this is the bottleneck, I will get exactly 10. But on the 3 links which are preceding on my path that link, I could get assigned more, but with no use, because if I get 20, I will send 20 megabit on these 2 links, and then when I reach that link, I will be seeing 50% of my packets statistically to be dropped. So what we are trying to do here is to have an end-to-end assignment which is compliant with the fairness concept, and with, of course, the availability of the bitrate on each link. Okay? So one possible, I would say one of the most popular fairness definition, there are other fairness definitions, which is basically formally stating what I informally described up to now, is called max-min fairness. And again, we are seeing this in the occasion of the discussion in the frame relay context, but all of these concepts are absolutely generally independently of the technology. So what max-min fairness is? This is a possible definition of fairness. And the bitrate allocation is max-min fair if it maximizes the bitrate allocation to flows who receive the minimum. So you try to push as much as possible, as high as possible, the bitrate of the flows which get a small bitrate. Once you cannot further increase this, then you will move to other flows and you will try to further increase the bitrate of those flows, and so on and so forth. So that's why it's called max-min. The objective is to maximize the bitrate that you assign to the flows that get the minimum. Okay? Again, the problem here is a bit rate assignment problem. We assume that we know everything. Link, node, flow, routing, etc., etc. Now, this type of definition has one couple of properties, or one property that we can describe in 2 ways, which is that if you have a max-min fair allocation, so suppose that you have an algorithm to obtain it, to increase the bit rate that you allocate to a flow, so suppose that you want to change this rate assignment, the only way in which you can do that is that if you want to increase the rate of one flow, you have to decrease the bit rate that you have allocated to another flow, which is getting less than this one. And we consider this to be unfair. We don't want to increase the bit rate of a flow which is obtained by reducing the bit rate of a flow which is already getting less than that. If you take the previous example, here in the second assignment, we are increasing the bit rate of this flow and this flow. You see, we move from 40 to 45 and from 5 to 10, but we decrease the bit rate of another flow from 5 to 0 that is already getting the minimum. And that's why this second choice is not max-min fair. In other words, no bitrate increase can be obtained without penalizing flows that are already receiving a reduced, a smaller allocation. Now, that's the definition. There is an algorithm that is well known and that we will describe in a moment that allows us to compute this rate allocation according to the max-min fair definition. to obtain this rate assignment, you must have a global network view. There is no local algorithm that is able to obtain an assignment which is max-min fair. So that's a kind of frameworks, kind of goal, okay? If we were able to know everything in instantaneous time and we were able to compute this max-min fair allocation in 0 time and able to distribute, to signal this information to the source, then we would obtain a network operating point that is the network operating point that we would like to have, okay? We know that this is not possible in practice for several reasons, but at least we have a goal, okay? The optimal solution under this definition that we are willing to compare against to see how far our solution is from this optimal ideal solution. So it's a reference. Any question up to now? Yes. Smaller or equal than the bit rate of this flow that you want to increase. So you take a flow which is getting 7 megabit, you want to move it to 10, you can do that, but in order to do that, you will end up reducing the bit rate of other flows which are getting 7 or less. This is what we don't want. See.
So in the previous case, we used the 40 megabit, give more to the one that was getting 5, perfect.
Say that again?
In the previous exercise, we could reduce a little flow 3 bit rate of 40 megabit. If, I don't know, possible in this kind of scenario, but to give more to flow 2, for example, 10, was good.
Yes, what I'm saying is that if you get a rate assignment through this algorithm, you cannot modify it in the way in which you are describing. So if you can do that, it means that it was not max-min fair. Okay? So if you have the max-min fair, if you want to change it, you can, but the only way is that you increase, but decreasing somebody which is getting less than that. If you have this possibility, it means that the allocation that from where you're starting for was not max-min fair. And this, for example, is what you can do if you take the second solution, right? Okay, so how does this max-min fairness allocation algorithm work? The algorithm has an input, the topology, yes? Okay, the topology, the link capacity, the knowledge about the flows, and the knowledge about the flow routing. So all of these elements are taken as an input and are taken as granted. We are not going to vary them. According to that, how can we compute this rate assignment? That's the idea. So, well, we start with an allocation which is 0 to all the flows, and basically the idea is that suppose that you have a fluid system, a fluid approximation, you start increasing continuously from 0 the rate of all of the flows in parallel until one link saturates. Okay? When the first one link capacity saturates, it means that the flows sharing that link are satisfied. You cannot further increase their rate in any way. So you will fix the rate for these flows end-to-end as determined by that bottleneck link. And then once you establish that, you will keep increasing again the remaining set of flows until a second bottleneck link pops up. When the second bottleneck link pops up, again, you will fix all of the flows sharing the second bottleneck. You will assign this rate, and you will try to increase the rates of the remaining flows, and so on and so forth, until all of the rates have been set. Not necessarily you will saturate any link. It depends. It depends on the link speed. It depends on the number of flows. You may stop either because you have saturated all of the links used by the flows, or because you have assigned the rate to all of the flows. Okay? That's the algorithm. Now, that implies, is it clear, the algorithm? Now, that implies that for any change in the input set, you should rerun these algorithms from scratch and recompute the new rates. And any change in parameters means any link speed variation. Well, it happens, but very, very rarely, right? You don't change the transceiver on a link very quickly, very often. Fault. A fault means that one link disappears, so you have to change the routing. One flows leaves, or one flows, new flow comes in. You have to recompute everything. This is much more frequently happening in real networks, okay? So all of these events, or if you change the routing, this is not so popular, not so common. Any change in the topology, link capacity, and flow routing implies that you must relearn from scratch this algorithm. Okay? And that explains why this is not a practical solution. Because even if you assume that the link speed is not changing very frequently, even if you assume that the flow routing is not changing very frequently, and both of these hypotheses are reasonable, unfortunately, the number of flows is instead highly variable over even a short time. So that will make it impossible to run an algorithm like that in a practical real network. Okay? So we can take it as a reference system. We know that we would like to obtain something like that, but it's not practical at all. It's just a theoretical solution only. Okay? So before we go, I will suggest you to play a little bit with this example. Try to find a maximum fair bitrate allocation to these flows, where the convention is that flow I is a flow which is source as Si and destination Di. So flow 1, for example, is composed by packets sent from source 1 to destination 1, from S1 to D1, flow 2 from S2 to D2, and so on and so forth. This is a very simple topology. It's called parking lot topology, and all of the links have 100 megabit per second speed, except for this first link here, which has a 34 megabit per second speed. Okay? And that's it. So we have one flow 1, which is doing this, you see. This is the path of flow 1. Flow 2, which is going in from through link 1 and 2 and 4. Flow 3 and 4, flow 3 is doing this path here. Flow 4 is doing this path here. And 5, 6, 7, and 8. 5 is just crossing link 3. 6, 7, and 8 are crossing link 4. Okay? So the question is, you have of course the answer in the next slide, but I will suggest you to avoid to look at it. The question is to try to run the previous algorithm in this scenario and see which results do you obtain. Okay? And then we will solve it together. You have a question? So try to solve it. When you are done, check with the result and see if this is correct or not. And then we will try to understand how we can solve it together. Is it working? No, you must, not you can. You have to. No, it's for now. to encourage you to try to solve it, this is one of the typical examination questions. Not on this example, of course, but so it's better that you are pretty sure that it is clear to you how the algorithm works. Salute. Viene, non viene, ritorna.
E so che però solo 3, e quindi l'altro dovrebbe essere il quarto, stato la prima perché è il flow. Però
Beh, devi fare il conto,
fa parte del passo da qua, quindi in teoria io dei 100 potrei togliere 7 sicuri, e quindi me ne rimangono 83, però poi devo togliere questo perché l'ho già considerato, quindi ne ho solo più 4, 2, 6, 7, l'8 su questo, sulla capacità che mi rimane. Dovrei dividere per 4 e viene 20 o 75, che dovrei allocare per il 2, il 6, il 7 e l'8.
So let's try to solve it together. Okay. Dove è finita? Okay. So let me copy the scenario here. Oops. Okay, then we have flow 1. Sorry, I don't see it very well. Okay, we have flow 1, which is doing this, right? Flow 2 is going straight forward. Then we have flow 3 and flow 4. Flow 3 is doing something like that. And flow 4 is instead doing something like that. And then we have 5, 6, 7, and 8. All of them going, flow 5 is doing this. This is flow 1. And then the other 3 are doing this. Okay? Flow 6, 7, and 8. And the speed are all of them 100. On these 3 links here. Except the first one, which is 34. So this is 100. And this is link 1 is 34. Okay. So this is the scenario. Now what we have to do? Well, we have to assign the rate to all of the flows. So flow 1, flow 2, flow 3, flow 4, flow 5, flow 6, flow 7, and flow 8. And how does it work? It works in such a way that we have 4 links here, which are link 1, link 2, link 3, and link 4. Okay? Okay, so let's start analyzing the situation. What we have to identify is which is the link which is saturating first. Okay? Now, the link which is saturating first is the link in which C, being C the link capacity, divided by N, the number of flows, is minimum. Correct? Everybody agrees on that? So if you consider all of the links, you take the at this point we have no rate assignment, so all of the four are 0. The first link that would saturate is the link in which C, capacity of the link, divided by number of flows, is minimum. In other words, if all of the links have the same speed, the first that saturates is the one which is shared by more flows. In this case, we have to take into account that one of those links has a reduced bit rate with respect to the other one. Okay? And indeed, if you do the computation, you will see that the first link that saturates is exactly link 1, which has only 34 megabit per second capacity, shared by two links, and you will assign to these two flows, sorry, shared by only two flows, and you would assign to these two flows 70 megabit per second. So link 1 is saturated, and the two flows sharing link 1 are flow 3 and 4, if I'm not wrong, yes, which get 17 megabit per second assigned, okay? And that's the first link that saturates. Now, flow 3 and flow 4 are bottlenecked. You cannot further increase their capacity, correct? It's not possible. So we have to examine the other three links now, starting not from the absolute bit rate available, but from the residual bit rate available. Because now the other flows, which are all of them already getting 17, because remember, we are increasing all of the flows in parallel, but they are not fixed, they can be further increased. But the further increase can occur only exploiting the residual bandwidth. I can assign to this flow what is left after this assignment. Clear? So what is left on link 2 after the assignment of 17 to flow 3 and 4? Which is the residual bandwidth on link 2 after this assignment? 66? Everybody agrees on that? And the residual bandwidth on link 3, which, if I'm not wrong, is this one here, if I'm not wrong. Residual bandwidth on link 3. Residual means after having assigned 17 to 2 and 4. Is still 100, okay. And link 4? Which is 83? 83. Okay, these are the residual bandwidth on the three links which are not already saturated. Now, how many flows we have on link 2? Allora, the number of flows on link 1 is, sorry, link 1 is set up, it doesn't matter. Link 2 is 4, right? 4 of which 2 of them are already fixed. So we have 2 flows that can increase their rate only. The other one cannot. On link 3, we have 4 flows. All of them can increase. There is no, and on link 4, we have 5, but only 4 of them. Correct? So which is the link which is going to saturate first in this scenario? Link 4, exactly. Link 4 is going to saturate to which bit rate? 20.75, if I'm not wrong, correct? So we will to assign on link 4, which is now saturating, 20.75 to flow 4, sorry, no, to flow 2, 20.75, 6 is 20.75, 7 is 20.75, 8 is 20.75, correct? Now, after this assignment, which is the residual bandwidth on link 2 and 3, we have two flows, sorry. We had flow 2 flows that could be increased, flow 1 and flow 2, correct? But now flow 2 is, so which is the residual bandwidth of link 2? No, it's 66 minus, okay, if you do this computation, you have to do 100 minus all of the rates allocated to all the flow, which is not what you did. You took the residual, which is 66. From the residual, you have to subtract the difference between 17 and 20 from the residual to compute what is left. You don't like this. Okay, let's do the computation another way. Takes link 2. On link 2, we have 4 flows, okay, which are 1, 2, 3, and 4. 3 of them are assigned 20.75, 17, 17. What is left is 100 minus the summation of these 3, which is, you have the 45.25, something like that? I don't remember what did you say. Okay, I did. Okay, doesn't matter. I was wrong. Don't worry. That's fine. That's the number. On link 3, yep. This 45, 20 and 75 is because this link saturates, and the flows that can increase their rate on link 4 are 2, 6, 7, and 8, 4 flows. So they are going to be assigned this value divided by 4. You have to do the computation. We did the computation. You take this number, you divide by 4, and you take 20.75. You take 66, you divide by the number of flows, you get a larger number. You take 100, you divide by the number of flows, and you take a larger number. So the minimum is the one that saturates first. Is it clear? Okay. So the residual on link 3 is how much? 100 minus? We have only flow 5 right here, which is left. So it's 39. But flow 6, 7, and 8, yes. 62 point something. So the residual is 47. 40. Okay. Okay, that makes sense. Okay. That's fine. And so now again, we have which is the one which is saturating first. That's trivial because you have one flow residual on each of them. So L3 now is going to saturate, and that will give the assignment to flow 5, which is 37.75. And finally, link 2 will saturate, which will give to F1 45.25, because you saturate all. In this example, we are saturating all of the links, okay, in this trivial example. Is it clear? So you start increasing all of the links. When your first link saturates, you fix the rate of all of these flows sharing that link, and then on the residual part of the available capacity on the other links, you will keep increasing, another link will bottleneck, you fix them, and so on and so forth. Okay? You will find all of those slides on the web. I'm uploading them. I mean, you can take the picture, it's not a problem, but you don't have to worry. Okay? Clear? Questions? Yeah, sure. Yes. $45.27 is because on link 2, which is this one, we have already fixed at that step the speed of flow 2, flow 3, and flow 4. So 100 minus these 3 numbers here, it makes it, I don't remember, it was 45, right, the problem? So if you make 100 minus these three, the summation of these three are already allocated raised, this is what is left on that link. Okay? And the same for link 3, the same reason. This is what is left, residual bit rate at every step, which is changing. Okay? And that's what you have to look at to understand which is the link which is going to bottleneck first next. You start with the residual bed. Okay, that's it. So that's this example. And that's basically it. I would say that even if it's a little bit early, we can stop it now, because then we have to start from scratch a different topic. We are starting to discuss now how to implement forward and backward congestion notification. But now we have in mind that any solution has this target. We would like to have solution that implements something similar to that, if possible, and also with a limited requirement of coordination. We don't want to have a centralized approach because it doesn't scale, it's not working. Okay? Because networks are too fastly changing, are too dynamic with respect to the possibility of having any optimal algorithm to run to solve this issue. Okay? Clear? Okay, so let's have a break now.